Okay, hello everyone. So today is Saturday, so we are going to study a paper. In the last few weeks, I had been so busy that I've been too busy to review any papers because I was trying to catch up with some deadlines. And I actually submitted one paper in November, and last week I was supposed to submit another one, but later we decided to put it in a benefit conference later in January. So let's go over this paper today. A very popular object detector for efficiency, which is EfficientDet, scalable and efficient object detection. So this one is the author is actually the same as the EfficientDet, which is for image classification, but this one is for object detection. So actually I learned a lot from this paper. Let's go over. So here the main thing, let's go over here. This figure actually summarizes the main performance of it's actually a family of EfficientDet. When you say EfficientDet, it's actually a family of object detectors with different scales, namely D1, D2, D3 to D7. And in terms of efficiency, so here x-axis represents flops, floating point operations, which is a matrix to evaluate computation cost. And this one is commonly used in vision, mainly because of many modifications in convolutions and so forth. And this dominates the computation, especially in GPUs. So this one is commonly used in addition to inference time. The inference duration is mainly, it's actually hardware dependent. So this one is invariant to hardware. Is mainly about it's more related to a network's parameters. But in short, this one is used to as a metric to evaluate a model's computation cost. So in the y-axis, which is the COCO average position, higher the better. For efficiency, so here we're aiming for efficiency. Then the community usually we want models to go this corner, top left corner. So models lie in near this corner works better. And apparently this family of models achieves better performance in terms of efficiency. And YOLO V3 is here. It seems that for YOLO V3 is designed for remaining in this paradigm. In terms of flops, a mass LCNN takes longer and high accuracy, but when it comes to efficiency, it's still there's some gap here. And so forth. Okay. I'm really surprised at NAS. So NAS is neural network architecture search lies here because it searches for an architecture that can also aims for efficiency. But it depends on the specific design and the constraint and the dimension that it cares about. Okay, so let's go to this one, the main contribution. So here, so first they actually propose a new. It's not just about the method to scale the model. That's the main contribution. In addition, they also propose a new architecture, which is a bi-directional feature pyramid network by FPN. This one, it's mainly about the way to aggregate multi-scale features. Let's go to get data. And the second one would be the main thing of scaling in terms of efficiency. So to scale, they consider the resolution, depth, width in terms of network for different backbones, feature backbone, and so forth as jointly. And this is the main thing here. While the rest method does not consider in this way, and that's what makes EfficientDet better. So let's go to here. Let's study a little bit more about some of the important related work. So here, again, the first one is the FPN bi-directional feature pyramid network. So why do they propose this one? Why don't previous models work well in terms of fusing multi-scale features? Well, most of them just sum them without a distinction. So it's like we have different scale of features. Let's say it's a feature 1 scale here and feature 2. The size of the box here represents scale. One of the easiest way would be just some confusion. This one, if they're in different dimensions, well, we can just for instance, for F1, we can scale it to be the same dimension like as the largest one. I mean, just for example, not exactly this way, the same way that previous work did. I'm just trying to illustrate one example. Then we simply just like it could be element wise summation, and then so that let's say the shape maybe so that the shape is identical to one of the features here. If we do some, I actually use one of the summations in my previous paper. And another one common one would be concatenation. Concatenation, which is not mentioned in the related work in this paper, but it's also a common one. Basically, we can stack these features at some in some dimension. You can define which dimension to stack, and then concatenate them. And this is another way to fuse those features. And then usually later we can have some other weight or some other layers. You could have some fully connected layers. You could have other things, or a different block, different stage, depends on your design. So here then basically it lets the network be later here to learn on top of these features. if you concatenate them or if you sum them out. So well, this simple way of summing them, the things that different features at different resolutions might contribute to the output, the fused output feature unequally. So unequally is then if you sum them, essentially you treat all of them equally. If you sum them, it's like you have a weighted sum, but each weight is 1. So then that's why they propose to use some learnable ways so that the network can learn some weight, can learn to reweight and learn the importance of each different input features, which makes this network different from previous one. In terms of why is it called bidirectional? Let's go to the graph directly. This one is actually interesting. Before we go to by FPN, let's go to illustrate some basic network first. So first one is the feature pyramid network. So we have P3 to P7 representing different scales of features here. So we are trying to fuse P3 to P7. Well, first, in feature pyramid network is a top-down pathway from A. So let's go to, just want to check one thing. Resize. So let's consider this one as input, a larger input, and let's go down a bit, just a little bit. Okay, I think here is enough. So when we have an input, and then when it goes deeper into the network, the feature size resolution will be smaller and smaller by a factor of 2. So and then if you go to P7, this is a very high level. It should be a coarse level feature when the resolution is pretty small. And then, so this one is represent this scale of features, and P3 represents features in terms of this large resolution. And let's go back here. So with that, let's go back here. Okay, then we have a pathway. So whenever we have a path, it means that there's some weights that we want to learn here. So from top down from here, then add this path so that the it learns some way to fuse these features. And for PA net here, they add additionally bottom up pathway here so that now we have both top down and bottom up pathway to learn to fuse these features in a better way. For NAS, for your network architecture search, however, this one is usually like what they learn is usually hard to be interpreted by a human, and this one usually results in an irregular network, and this was very weird. But anyway, So then what the authors propose is that in addition to top down and bottom up, they add one more path, which is in the same scale. They add this one so that they have this bidirectional and then feature aggregation fusion network. And they remove the here mainly here and here mainly. The reason is they mention is that if there's only one single node here, then it means that it contributes less to fusion features. So we do not necessarily need them. Then we just remove them. That's the intuition in the paper. I'm still trying to understand. Okay, there's another one interesting here. So in terms of fusion, since we are trying to learn the weights, then one a straightforward way would be to have a weight multiplied by each. So each weight, each each input has its own weight. So that we to let the network learn. However, this is unbounded, which means that W could range from negative infinity to positive infinity, which can result in unstable tuning maybe, and later if whenever we go some infinity, then we are no longer able to change the network anymore. To do that, you can think of using like softmax, so that to normalize the weight, so that the range is from 0 to 1 instead of like negative infinity to positive infinity. So now we have 0 to 1, and this ensures that our chaining can proceed. Well, the another issue is that since this one is exponential to the power of W, so this one is a bit, I mean, for hardware computation for the architecture, there's some floating point if we compute this one, which is a little bit slow if we were tuning on GPU. Another one would be to use so instead of some of the explanation of to the power of W, they simply just use here without the explanation here, so that we can faster so it's like in each part we do not need to compute the E, which is a little bit slow for GPU hardware. We simply just add some all the weights and then do the normalization, and then we add some small number of epsilon. This is mainly to avoid numerical instability. This is a common check in when you change the network. If so, for instance, if this happened to be 0, then we no longer be able to proceed training anymore. So when we add epsilon, then we ensure that there's some positive here, so that then the program won't stop just because it happened to be 0 here, and learn from my machine learning class. And thanks to my instructor. And they also use depthwise separation convolution. Maybe later I can have another video to talk about this. This one's interesting. This is a trick to it's mainly a trick in terms of for more efficient convolution computation here. I can talk about it later. And then let's go. Okay, so recap. The first one is the by pyramid feature network. The second contribution is the scaling method. So let's go to scaling. So they propose compound scaling. Previous method, user just focus on a single row limited dimensions. Then what the authors propose to have a single compound coefficient phi and jointly scale up all dimensions. And this is another main contribution here. The way they do that, so they use the by FPN as the backbone, and then they scale many in terms of width. Width is actually the number of channels, and they also depth, and also depth is meaning the number of layers. So for width, for scaling width, they actually scale in exponential way. I'm still trying to understand why. If someone can explain, that would be great. And in terms of that, they scale it linearly. And then let's go down here. Even for depth of bounds and resolution. Even for resolution, they're also scaled in a linear way. Okay, then I think that's the main message that we can learn from this paper. The rest is mainly the details of the comparison and so forth. Okay, yes. Okay, that's the main paper here. Let me go over the next one later. Thank you for listening today.